Vice Chancellor Sir, Professor G. Damodar Sir, to launch this webinar and speak a few words on this occasion. Thank you, sir.
Thank you, Professor Kavita. Dear participants, Corona has made us forget the difference between working days and holidays. This webinar is fixed as per the convenience of the speakers without looking at the calendar. So at the outset, let me greet our Muslim participants. Eid Mubarak, a very happy and peaceful Bakrid. No shadows to depress us, only joys to surround us. This Bakrid festival symbolizes supreme sacrifice of Ibrahim, an ardent devotee of Allah. He was prepared to sacrifice his son. Though we may not be so generous or magnanimous like Ibrahim, a little sacrifice that we do gives us a lot of satisfaction. Hope this festival will make us realize the value of sacrifice and make us kind-hearted, caring, and sharing. Well, coming to our webinar today, I'm pleased to launch this seventh webinar along with our dynamic registrar, Professor M. Ravinder, distinguished vice presidents, Mr. Engala Vikram Reddy and Dr. C.H. Satvika, co-chairperson of Vishwa Bharati Education Society. Dear participants, we have already conducted 6 webinars on different topics. And now this 7th one is being organized by our very active research-oriented Department of Chemistry. On behalf of Chaitanya Deemed University, I welcome all of you to this webinar. Our first speaker, Dr. P.K. Jain, is the scientist and head Center of Carbon Materials, Hyderabad. I'm told he will speak on nanostructured carbon materials and their applications. Welcome to you, Dr. Jain. I also welcome our second speaker from America, Dr. Kiran K. Somalingapuram Sai, Assistant Professor, Department of Radiology and CTS, USA. He is going to speak on PET imaging of novel biomarkers for early detection of neurological disorders and cancer. So welcome to you, Dr. Kiran Sai. Appreciate the efforts of the coordinator of the webinar, Professor S. Kavita, Head Department of Chemistry, assisted ably by Professor B. Prasanna, Director of Research, and Lieutenant Dr. Kavita of our university. My good wishes to all of you. A happy Bakrid to Muslim participants once again. Thank you. Over to Dr. Kavita. Over to the registrar.
Good afternoon, all. I'm very happy to know that our Department of Chemistry is organizing a webinar, an international webinar on 2 important topics. One is PET imaging of novel biomarkers for early detection of neurological disorders and cancer by Dr. K. Solingapuram Sai Garu. And second topic is nanostructured carbon materials and their applications by Dr. P.K. Jain Garu. Welcome to you, sirs.
Thank you.
The theme of the seminar is relevant since it focuses on the challenges and issues in chemistry and biological sciences to create a research ambience among the students, research scholars, and faculty members. It is a great pleasure that the potential academicians and persons from industry will be taking part in this webinar. Of the opinion that the deliberations in the webinar will enable the participant to solve the unknown challenges and provide us better future. I congratulate Professor S. Kavita Madam, Principal, Head of the Department of Chemistry, and Professor B. Prasanna, Coordinator of the webinar, research scholars, other faculty members of chemistry, students of chemistry, and organizing the webinar, which provides an opportunity for the fruitful interaction during the deliberation. This helps to acquire the knowledge and skills on the theme of the webinar, and I wish the webinar a grand success. Thank you. Over to Professor S. Kavita Madam. Hello? I think she is. Prasanna sir, please begin the webinar.
Yes, sir. Sorry, I had a technical problem because it's heavily raining out here in Hyderabad. I would like to invite the eminent speakers, and I would like to also thank the patron, the guests of honor, and the registrar and the vice chancellor and the coordinators for organizing this webinar on the topic nanostructured carbon materials and their applications. And I'd like to extend my special gratitude to the speakers and Dr. Kiran Garu. I think it's early morning in the US. Thank you so much for giving your time. We look forward to a beautiful webinar. Thank you so much. I think we can start the webinar right now. Kavita madam. Yeah, please go ahead with the.
Hello? Prasanna sir, please start the webinar. She is in unmute, she is in busy. Just go ahead. Prasanna sir. Sorry.
Can we have our first speaker?
I think first speaker is Kiran sir.
Sir,
may it is right? Kiran sir.
First speaker is Professor, I think Dr. P.K. Jain.
P.K.
Jain is.
Sir, I'm here.
Okay.
Okay, go ahead.
Okay. Thank you, sir. Thank you, Vikram Reddy, sir, and the Vice Chancellor and Registrar, sir, for giving a valuable message on this webinar. Now, I feel my privilege to introduce our eminent speaker, Dr. P.K. Jain, Scientist G, Head the Center for Carbon Materials, ARCIDST, Hyderabad. His topic of research is based on carbon composites. So he's interested in following research areas: exfoliated graphite and its products, synthesis and characterization and applications of nanostructured carbon materials, and acting polymers, structural nanocomposites, carbon fiber reinforced composites. All these research areas which sir is interested is now upgoing product works which are being held in on the different universities, which is helpful for all the participants to upgrade their knowledge regarding the research. Not only these research areas of interest, sir was also awarded BD Vanguard Award by Indian Carbon Society, New Delhi, and Voice Cast Fellowship from Government of India. Worked as visiting scientist in Institute of GAS National Academy of Sciences, Ukraine, and awarded Best Scientist Award in Physics 2016 by Pearl Foundation Educational Excellence Awards to Higher Education in India 2016, and Best Scientist Award by Academic Brand Award 2017 NCR Delhi 2016. And he also has membership with professional and scientific bodies as Joint Secretary. In addition to this, Indian Carbon Society is Joint Secretary for Indian Carbon Society, Aeronautical Society of India, Material Science Society of India, and Indian Society of Materials Processing and Engineering. above all, in addition to all these, he is reviewer for many peer-reviewed journals. This is a very important, which is for all the research continuing participants, or even for us, because we have to have more and more number of journals to be in peer-reviewed journals. Now, I invite Dr. P.K. Jain, sir, to present the lecture on nanostructured carbon materials and their applications. Thank you, sir. Now I hand over to you to continue your lecture, sir.
Thank you. Thank you, Dr. Kavita, for a wonderful introduction. Let me on the outset thanks Dr. Damodar Garul, Mr. Raindra Reddy, and all the university staff, everybody, those who have given the opportunity. Now I'm sharing my screen. Just let me see. Share. आयुषी बेटा इधर आना शेयर कैसे करेंगे इसको शेयर कर दो हाँ आ गया हाँ प्रेजेंटेशन F5 इसको ओके कर दो इसको okay now screen is visible to everybody.
Yes, sir. It's visible.
Okay.
Yes, sir.
Right.
It's visible.
Such 1 or 2 minutes sometimes takes time to. We are not that convenient. We are initially.
It's
in
visible.
earlier days we used to do with the OHP projectors. Then it has come the PPT. Now it is a webinar where the screen is shared anyway. So slowly we'll get accustomed. Now once again, thanks to the university. And especially thanks to Dr. Damodar, Dr. Kavita, and Mr. Special thanks, very special thanks to Mr. Raindra Reddy, who was our ex-student. Anyway, now as it was told, my topic is nanostructured carbon materials and their applications. I'm working in Center for Carbon Materials. So this center is located in Hyderabad. When you go to airport on the way, Balapur. We are very small. It's a autonomous R&D center for Department of Science and Technology, Government of India. We are about 160 employees. Out of that, 65 scientists and 60 technical staff and 45 administrative staff. But we have a very unique mandate. It's not like a normal institutes where research people do, and then it's not like university or the production unit, but we are having a special mandate where we have to develop a high performance materials in the process for the niche market. And then ultimately this all these products and processes is to be demonstrated at pilot scale plant. And then eventually this will be transferred to the industry. Unless, so most of our activities are industry driven research, which we transfer it to the industries for the commercial exploitation. And many times it is not the commercial, sometimes even for defense or for space, where the commerce angle is very low, but the importance is very high. We have a beautiful campus, you can see very greenery. But in our institutes, we have divided our whole ARCI into many centers: Center for Nanomaterials, Center for Ceramic Processing, Non-Oxide Ceramics, Laser Processing, Center for Engineering Coatings, Solar Materials, Sol Gel Coatings, and I'm looking after the carbon materials. We have a very strong characterization center. You name any characterization technique in this, whatever you find in any areas, we are having that in our ARCI. Two centers are working in Chennai, Center for Fuel Cells and Center for Automotive Materials. And we have a unique center called Center for Technology Transfer. This center will act as a bridge between the technical centers and the commercial industries, because industry is having a different type of requirement, expectations, whereas we understand the more science and technology, and industry understand the money part. So there is a how to bridge those aspects, where legal aspects or the copyright or all those things the Center for Technology Transfer look after. Till now, we have transferred many technologies. Here is some list of the technologies which we have transferred. Here is again continuation. The last two technologies which were in the list, I was the project lead, the exfoliated graphite and the operation board for metallizing industry. I was the project leader for this. Now coming to the materials always now. If you go into the material research in mankind, this is from stone age to bronze age to iron age to chemical age. You will find every age, the civilization is driven by the materials, whether it is stone or the bronze or the iron or the chemical or the nuclear material or composites. Now we are in the era of nanomaterials. So this is a materials is since beginning. It is not a new. The materials are always a very important aspect of mankind and the civilizations since beginning. If you see, just see the last century also, we have seen the vacuum tube technology, where we have seen the television, radar, and radio. The first half of the century. The second half of the century was the semiconductor technology, where we have seen the cell phones, computers, transistors. Now this is the era of nanotechnology. You can just hear worth mentioning the semiconductor technology. This is the technology which has made Japan as a superpower, a semiconducting material. Based on this, the electronics and all those things, Japan is a country which does not have any natural much natural resources, but still it is a very strong economical power in the world, technological power in the world, and a very strong country. So just because of the materials development, so materials are always important. Nanotechnology is a era where all countries all over the world, people are engaged into the nanotechnology research, because this is a possibility. Here is a possibility to come out with a unique combination of a material which will be like a work as a multifunctional, because as we are growing up, we want everything miniaturization, the everything is happening in a very small, a small materials can should perform a multifunctional aspects. For example, if you see those who are of 40 years plus, just 20 years back, these are the household items in everybody's house, whether it is radio, movies, VCR, video, alarm clock, telephone, fax machine. These are the common household items, but these all items are not there now. Where they have gone, how they are performed, who is performing their function. Now this is here, a smartphone. Everything about 1400 to 1800 kilogram has disappeared, and it has come into hardly 200 grams. So that's how, because the same performance, each materials is performing a multifunctional. The expectation from materials has gone up. Now, when it comes to nanotechnology or nanoscience, whether it is a nanotechnology or nanoscience, we have to understand first. If you see the technological aspect of the nano technology, even just a few centuries ago, in the 4th century also, we people have seen in Europe there was a Lagerfeld cup where the gold nanoparticles are dispersed in glass. When you pass a light, you can see the red color, otherwise it is a green color. There are a lot of glass windows and other things which is having a nano particles inserted into the glass. So even the old artifacts also, the nanoparticles were found. Even in the old, very old Harappa or Mohenjo-daro civilization also, the nanoparticles were there. And even recently, means those who knows, this is a very common in our India, the kajal or katuka, which is used since centuries. We don't know since when our ancestors have started. Now all these things are the applications of nano. But now, why all of a sudden for last 2-3 decades the nanotechnology has come into the scientific line? It is not the nanotechnology, it is the nanoscience. Basically, now we started understanding the science part of the nanotechnology. So nanotechnologies were being used since centuries, but we were not understanding the science because we were not having the equipments, the equipments which can see the atoms. Now we have a high and transmission electron microscope which can see the nanotubes, which is in the size of nano. So apart from that, there is a big fuss about the nano also, because nano is a word. If you just type into any search engine, you will find very high number of hits, about few millions hits will be there. Why it is so? Because it is having an impact in all area of the applications, whether it is electronics or space or defense or the security or the sports or the cosmetic, pharmaceutical. You will find the applications of nano in everywhere. And apart from that, a big money is involved. Now all countries have started their nano mission, where the people were asked, the research groups were asked to do the research on the nano. So many research activities are happening across the world. And this is just to start with that, how this nano is now like how our science is driving, because driving force can be any fictions, our fictional movies, where our mythological movies, where you can see the Superman, he is having a jacket which is having like a bulletproof jacket. Now 40, 50 years back, these were fantasies, but now we are having a material which will act as a bulletproof jacket. The spider net thing concept. Now people are working onto a materials which can act as a spider net. This is like a hollow man. This is like a invisible material. The materials are invisible. The people are invisible. If you give a coating onto them, anyone, it becomes invisible to a particular wavelength. Now you can see even a mythological concept also, like our Hanuman can fly. So there are researches going on who can become very small to very big. In our mythological books are also written. Spider net, for example, is a looks to be simple, but it can impact. It can stop a bullet, and which is having a speed of 329 meter per second, and the maximum weight is hardly 2.6 gram. So such a wonderful material, the spider net, and all over the world, people are collecting the spider net and put together. It is about the Russian countries are very advanced. They are having about 600 grams of a spider pulp. They are producing it. Now, nano in our life, it is very important to know that whenever any activity start, if it is not finding any new applications, or it is not finding application for the society, society is very cruel. It does not give any support to any of the scientific these things. Like 25 years back, there was a field called superconductivity. All people all over the world, people were working on superconductivity, but unfortunately or coincidentally, it could not find a penetrating into the scientific social applications, which was supposed to find out from the superconducting materials. So people have forgotten. Similarly, if nano will not be able to give any social impact applications, even people will forget the nano. But nano has started giving. Now there are a lot of sporting goods are there, golf clubs, tennis rackets, the paint and coatings, which is based on the nanomaterials. The computer chips are there, the nano composite plastic, the pharmaceutical sun creams, nanotextruders, wound care, cosmetics. You name any field, you will find. I'll just show you some few examples like here. If you see the nano coatings given into the washing machine or to the fridge or even to the gas stove, a few years back, any spatula or any knife will fall. Now these are scratch resistance coatings are there onto the gas stove. You will not find antibacterial coatings are there into your washing machines. So now you people find a lot of applications of nano in apart from that, like cosmetics. You just apply the cosmetics in a nano form, you will find it will act as a very fast in pharmaceutical industries or cosmetic industries. Now this is a corona period, as our Dr. Damodar has told. So people are looking for a filtration units like filters, air filters, water filters. Here also nanotechnology plays a very important role. It can be like used as a filtration mask or something. Now this N95 marks or different cloth marks or all these marks are based on the different pore size which can stop different type of microbes or the viruses. There are special coatings that's given into onto the surgical tools, because if any rust is there onto the surgical tools, it is no longer a very good. So you require the tools which is having a rust proof or rust resistance. The tiles are there which is having a hydrophobic coating, so the water will not adhere with that. So if it is a small house or something like a 1 floor 2 floor, no problem. But if it is a skyscrapers are there, very high, many multi stories are there, how to give a coating? So in place of give these things, you just put a panel which is having a hydrophobic coatings, and you don't require to clean it. Like easy to clean coatings are there, which is used in our like in a Burj Khalifa or big buildings. As I told you, the sun creams, UV protections, the nanomaterials are always there to protect the skin. In the food packaging industries are also having nano coatings materials. Like if you can just imagine the packaging industries, all our chips packet is, all these chips are having an internal lining of aluminum foil. If in chips you can just compare the cost of a chips is total is about 60 to 70% comes from only from the packaging part. The ingredient, the potato and the processing is hardly 40%, but the packaging contribute to the 60%, because if your packaging is not good, you cannot sell those chips. It is no longer, people will not find it the tasty or the crispiness. To retain those crispiness, the packaging is very important. Even the Indian foods, which is very popular in the Europe and USA, if you want to export it, you require a special packaging. The pharma companies are looking for a particular drugs has to be stored into a particular temperature, like 20 degree at plus minus 4 degree. So you require a different type of packaging which can retain the temperature, which can maintain the temperature by the nanotechnologies. There is a possibility with this nanotechnology. In the biological and the targeted drug delivery, like in especially the cancer cells, which is not very good. But when people go for a chemotherapy or something, it damages the good cells also, and it affects the body, like hair fall, the swelling of a body, unexpected, unwanted things happen, results comes, and not only just to treat the cancer cells, people have to undergo a lot of a pain. The body physics will not be good. So to overcome that, a targeted drug delivery where the only cancerous cell will be treated. This is happening, is possible because of the nanotechnology. Now, corona, but before corona, there used to be people used to talk about the chemical warfare. If any chemical warfare, now this type of dresses, we can see it is very common in the corona period because PPE kit. But just 6 months back, these are not very common dresses. But if you go to in a border area where people have to have a fear of a chemical warfare, people are having such type of dresses which can protect their skin, which can protect their body against all chemical moieties. So different type of, like you can see these canisters are there which is filled with carbon, which can, when you take breathe, all the chemicals can be absorbed into the activated carbon. This is a like a special type of, if it is a nanomaterials, it can penetrate into your body and then heal it faster. Like a few years back, you have seen in the cricket ground, people used to apply the sun cream, but now they are not like our, whenever people used to go to Australia or Australia used to come, they used to apply the sun cream which were more visible. But now people don't apply. It doesn't mean that sun has become weak or the the players have become very strong. It is simply the cream what they apply is not visible. It is like a nanoparticle dispersed cream which is not visible to because the wavelength is different. As I told you, the hydrophobic coatings are there you can apply into the cloth, and then easy to clean. If your cloth is not having a ability to affinity to attract the dust, you can use the cloth. It will not give the stinking smell or something. You can keep your cloth for 3 to 4 days. Otherwise, every day you have to wash it, because of our tropical country, it is sweating more. So you can preserve the more water which can be used. Water is a very precious commodity which can be used for the more other very good applications, rather than washing the cloth or washing the any car or something. Here one example of nanotechnology. This thing just, it will change the color. Now why it changes the color? Because the different particle size of a cadmium selenide, this thing there, so one can see. Now all these things are the size particle. Now why nano is very important? If you take a very small cube of a 1 centimeter, the surface area is about the 6 centimeters square. But if you take this break into 8 pieces, and then the surface area increases, and each pieces if you break into 8, so if you repeat this cycle to 26 times or 24 times from the same cube, you will get a material which can cover the sports like a football stadium. So same material will have a very high surface area when it is into the nano size. So your surface activity, the requirement of the materials have come down. It can perform a multifunctional role when it is there in nano form. Apart from that, the surface to volume ratio, if you just see, it also changes. If you take a 10 micrometer diameter particle, the surface area is 0.22 meters square per gram. If you change into 50 nanometer, the surface area almost it becomes 20 times more than 44 meter. But ultimately nano is only size. So one can get this size either by top down approach or by bottom up approach. These are the only two approaches one can get a size of a nano. In top down, you start with the bigger materials, go on milling it, you will get a particle which is of your desired size, but it has its own disadvantages and advantages. Advantages is it is very less expensive. Any small lab can also have a ball mill or any milling material machine. You can reduce the size. You can increase the large scale process. It is well old but well established process. You can get it 2 to 20 nanometer, but the disadvantage is you don't have the control over the size of this thing, the particle size distribution, the morphology. Irregular nanoparticles, introduction of defects are possible. All those things are possible. There is another called bottom up approach, where like in a sol gel, you start with any material sol, and these things, these are all depending on your applications, one can select. So in this process, one has to use very high costly raw materials, but sometimes they are toxic also. So one has to select what type of process they want to adapt. Now, this is a very importance of nano research. The nanoparticles exhibit size-dependent properties that are profoundly different from the corresponding bulk material. Like in a bulk form, gold is yellow, but in the nano form, the gold is not yellow. The density of a carbon is 2.26, but in nano it is 1.5. The strength or the melting point of iron is very high, 1400 plus, but it becomes 700 or something in nano. The aluminum becomes pyrophoric in nano. So the electrical properties, magnetic properties, mechanical properties, optical properties, chemical properties, all these properties is no longer same when it was in the bulk form. So it means what? Other than the name common, like a carbon or a iron, what are the things common? So we have an opportunity to redefine or to restructure the periodic table where the different set of properties are available for a particular material. Now that's the interesting part, because carbon, people, those who are mechanical department, they must be knowing the modulus of a carbon was 1060 GPa. Now people are having a carbon nanotubes or a graphene which is having a strength or a modulus of in terapascal. So all of a sudden a quantum jump in the all properties have come. whether it is mechanical. So the size have reduced, the properties, the same material will perform all the multifunctional properties. Like in our day-to-day use, we are using a multi-grain atta. Why we are using multi-grain atta? Because our limitations is that we cannot take more. We want the same atta should perform. They should give the protein, the vitamins, everything, which is not only possible by one particular grain. That's the reason now a same material has to work as a multifunctional: electrical, magnetic, mechanical, optical. Otherwise, earlier people were for mechanical properties, they were using different set of materials. For thermal properties, they were adding some other material which can improve the thermal properties, or the chemical properties, or the optical properties, or the chemical property. So that's a very important. As I told you, this is an opportunity to redefine the periodic table. Now coming to the carbon materials, carbon is always a very important material. It is a material which is having a multifunctional role and the shape, properties. Like diamond is hardest material in the nature is diamond. It's so hard that all the hardness is in the with respect to the diamond. The carbon, the coal, you just name it, and all properties. One is white, one is black. The carbon nanotubes, the graphite foams. You will find activated carbon, graphite. There are variety of carbons are there, and each are having a different type of applications. Each are so independent from each other that each is having its own subject of study. We will not talk about many other things. We will talk about the graphitic carbon. So graphite is a material which is having a very unique properties, like it is having a low density, chemically inert. You take this graphite and dip into any chemical, nothing will happen. It is having a high thermal and electrical conductivity, low coefficient of friction. Low coefficient of friction is there, and it is having a self lubricity, biocompatible. You make a 100% graphitic material, you insert in your body, nothing will happen, and it is biocompatible, means it does not react with the blood cell. And one of the very important properties of graphite is it is the only material which can retain strength at high temperature. In the whole periodic table, you increase the temperature, like in a steel or metals, you increase the temperature, the strength will be very low. But if you take the graphitic carbon, whatever strength at the room temperature, the same strength you will find in the high temperature also. Say 2000 degree also, you will find the same strength. So owning all these properties, this was a very unique combination of properties. But mankind has started using a carbon into a fibrous form. So there were different grades of fibers were there: polyacrylonitrile, the pen fiber, pen carbon fiber, pitch-based carbon fiber, the vapor-grown fiber, the rayon-based carbon fiber. Just for as a comparison purpose, one can see the human hair is in the vertical form and carbon fiber is crossing here. So carbon fiber is in the range of 6 to 8 micron, whereas human hair is about 100 to 150 micron. But now people are talking about not only the human hair, even the nanofiber, which is having 100 nanometers, or even sometimes nanotubes, single wall carbon nanotubes, which is 1 nanometer. This is the different texture of the carbon fiber. Now, how carbon fiber is processed? The carbon fiber is processed. You start with a polymer fiber. It's in a special furnace. You stretch it, and that is called thermostretching. And after stretching, this will become stable. And this stable fiber is carbonized. Carbonized means heat treatment up to 1000 degree, and then graphitized. This graphitization means heat treatment more than 2500 degrees centigrade, and then process, and you will get a carbon fiber spool. The other route of making carbon fiber is the pitch base, where the petroleum product coal tar pitch is used, and spin it in a fiber form, and finally again you will get a similar type of carbon fiber. These are the different type of carbon fibers. Like as I told you, in the composite applications, the fiber is this is the reinforcement and the main load bearing material. So not only the unidirectional, even there are requirement for bidirectional or tridirectional or radial directional. There are a lot of applications which requires even multidirectional, because you want to exploit the properties in that particular direction. Now, salient feature of carbon fibers based or graphite based this thing is thermally conductive, energy storing materials, heat resistance, they are strong, stiff, and where all materials fails, carbon will stand. It is having a unique combination of properties that can be tailor made. Some of the few examples in a composite form of carbon, you can see this in rocket nozzles, nose tip, missile nose tips. This is the nose tip whenever our missile goes into the space, when it enters it, and after this faces that this particular material faces a temperature of 2500 degrees centigrade. Now 2500 degrees centigrade, which material can withstand? There is no material in this universe which can withstand that temperature. So all our success of our all missile programs, all our space programs, our success depends on the carbon material, how strongly carbon is working for them. There's a reason. It is a strategic material, very strategic material. There is a special labs are there in DRDO. There are labs are there in ISRO, which is exclusively working on carbon materials. So this is the rocket missile nose tips. In any aerospace industry, you will find these are the composite materials which is having, and because you require in aerospace materials a lightweight material and perform a highly structural strength is required. So composites serves that performance where the strength is very high, but the weight is very low. In aerospace industries, weight saving is very important. Each kilograms saving is a contribution to the aerospace industry. This is a brake pad applications, like just imagine an aircraft which is having a few hundred tons of weight, and speed is about 300 kilometers in a runway. When it has to be stopped, the kinetic energy generated by this aircraft is very, very high, and the whole load or energy is taken care only by this brake pad. You can see the graphitic die, and in our turbine engine applications, you can see the die. If you want to press any materials at 2000 degrees centigrade, your material, ceramic or something is there, but you require a die which should able to withstand 2500 degrees centigrade. There is no material you can make it a die from that other than graphite. These type of, the last one, the black one, you can see the center one, or this long one is the electrode. If you want to, these are the electrode which can be used in our metal industries. 2000 degrees centigrade, 2500 degrees centigrade you can achieve by which heating element? And other than graphite, those who are working in high temperature furnaces, they may be knowing that after 2000 degrees you require a graphite electrode. Apart from that, there are some common applications, like in our badminton or tennis rackets. They are very light. Those who play the badminton, they may be knowing the nano speed or carbon based, Carbonex. All those grades are there from the Yonex. The baseball, the bat of a baseball, or a golf stick or hockey stick, or even tires are black because active carbon is used there. Even though this looks to be very small, the graphite brushes, but from mechanical energy to electrical energy conversion is only happening of the graphite. So this particular is a very small component, but without that motor, you cannot transfer the current. So brush is a very important, very, very, very highly moving item. Is a hardly 2 rupees, but 5 lakhs to 60 lakhs pieces, 50 lakhs to 60 lakhs pieces per month some companies produces and introduce into the market. This is the activated carbon, which is in our AquaGuard or something, and in water filtration. Every 6 months, engineer comes and changes only this activated carbon. These are, now we are working on the graphite foams. These are the foams which is used in our different type of applications. This can withstand very, very high temperature and used as a porous material. Apart from that, as I told you, These are the few other applications. These are the composite which is used in our like in place of a plasters for animals or something. The tissues, even this all our face packs. The this thing toothpaste. You will find activated carbon. Earlier, 50 years back in our India, people were using the coke, the activated carbon powder, and the salt for this cleaning the teeth. Now this is activated carbon. From the coke carbon it comes. People use the coconut shell or something to make it, and then it is having a very high surface area which is used for different type of applications. Now these are the some list of the applications in a compiled: the brake disc, rocket nozzle, nose tips, EMI shielding, nuclear. Nuclear is you require a material which is having a safety factor of more than 2 or 3. Now, the first wall of a nuclear reactor will be always with a graphite, because nuclear radiation, no other material can absorb. By its structure, graphite is used as a first wall in the nuclear reactor. The engineering application, the dies and mold, the turbine blades, cutting and abrasive, building materials, chemical, the hydrogen storage, all batteries, fuel cell applications, biomedical, all these applications you just see this, you will find a graphite. Now coming to the carbon into the nanostructure.
మాణిక్యాలరావు చనిపోయింది కదా బీపీ దేవాదాయ శాఖ
The carbon nanotubes.
అమ్మా మరి కూతురుతో జాగ్రత్త దయచేసి.
Okay, this is the carbon nanotube where the single layer of a graphene is rolled into a seamless by nature and then converted into carbon nanotubes. This is having how this nanotube has taken a fold will decide the properties such as like the whether it will be armchair or zigzag. It will be having a different properties like in a semi-metallic or metallic depending on the bonds. Now you see why these nanotubes are very important. You can see a combination. Young modulus is 1 terapascal, tensile strength is 60 GPa, steel is 2 GPa, conductivity of CNT is 10 to the power 9 ampere per centimeter square, whereas copper is this. Now in the combination of all these three, so in nanotube you will find that by it's become the carbon has become a very favorite material for very many applications. Some of the applications in like lithium batteries, this will act as a anode, where the intercalated compound can go, and the charge, like if you see our batteries application and other places, this carbon is playing a very important role. In our fuel cell application or the hydrogen storage, the nanotubes are considered to be for good for hydrogen storage. However, the repeatability was a challenge. Reports were having from 0.2% to very high percentage. So because of a wide range of non-consistent result, people have not working, but these were the once upon a time of the probable candidate for the hydrogen storage. This can be used as a cantilever, nanobalance, or it can be attached, the protein can be attached with each nanotubes. Now it can be act as a probe into our high-end electron microscope like FESEM. The SEM has converted into field emission effect because of this probe. The carbon nanotube is acting as a probe material into a high-end microscopes. It is also using it as a nanoelectronic tongue, like it can give a particular resistance with a different chemical compositions. So you can quantify the taste or quantify this is useful into our beverage industries or the coffee or alcohol, where you want to have a particular taste. Electronic applications are also of nanotubes are there. This is like it can act as a actuators. It will be like you just give it, it will swell it or something. It is, as I told you, the hollow man. I have shown you the picture. If you give a coating of a carbon onto a missile, this missile becomes invisible in a radar. So it becomes like invisible to our enemy's eyes. So indirectly, it has become like a hollow man. The idea is like that. Sorry. So now there are some list of some few applications of carbon nanotube. These are here as a reinforce in a metal matrix or polymers, ceramic, carbon metals, biomedical surface coatings. You just name it, you will find. So these are the different techniques to make carbon nanotubes: arc discharge, electrolysis, CNT, CVD, sonochemicals. Many things are there. We have in our center the arc discharge, where the two graphite electrodes are taken and they pass a very high current, and you will get a deposit. This is called a cathode deposit, and in this deposit only a lot of nanotubes will be there. In the CVD reactor, CVD, here the carbon nanotube grown into a different type of alignment. You can control, like a vertical aligned carbon nanotubes can be developed in this reactor. This is a arc underwater. The arcing of a graphite electrode is done underwater, and one can grow the nanotubes. Even laser ablation, this is a laser ablation method, and this is a fluidized bed reactor where the carbon source and the catalyst is fed, and one can get a carbon nanotubes. Now, depending on the growth mechanism, is either it can be root growth or tip growth or a mixed growth, where you require a catalyst to grow these nanotubes, transition metal like yttrium, iron, or any nickel. So either these particles will be onto the top or onto the base, depending on your parameters. One can get a different type of this thing. Now, this also well aligned nanotubes. Rajendra Reddy must be remembering this, because he has worked on aligned carbon nanotubes, and with the closed end, open end, whatever way you want, you can grow in the CVD. Now, different patterns you can grow into this thing, different structures you can grow. We have a high-end reactor also. But in arc discharge, apart from nanotubes, you will have a lot of other carbonaceous materials. So those carbonaceous material has to be purified. This purification is done in the acid treatment and thermal treatment and physical filtration, mechanical, thermal, and the chemical, and finally you will get a purified carbon nanotubes. This can be quantified by TGA, and under a transmission electron microscope, one can see a very high grade of carbon nanotubes. Now, once the carbon nanotube is there, it is not simply you can use it as it is. You require a different type of processing, functionalizations. Otherwise, if you want to disperse into any solvent, it will settle down. So you have to have a particular type of size and the functionalization to make it disperse, and then only it can find some applications. We are working onto the sensors and different type of polyaniline composite is also used, EMI shielding. One can grow the spiral carbon nanotubes also, because they are act as a nano spring. We have, like in a composite applications, you can just see a polymer, epoxy polymer is completely yellow, but just by adding a very low percent, 1 weight percent, it is so high, surface area is very so high good that it has become a complete black. And this is the properties of a pure, this thing is 54 MPa or 60, 70 MPa, it has become almost 200 MPa just by adding 1% CNT. So properties can be enhanced in a big way. Now, as I told you, distribution of nanotube is also a challenge. It is not distribution, it is called dispersion. If nanotubes are distributed in a different scattered way, then you will not get a very good properties. You have to have a dispersion where all the nanotubes are scattered in such a way that the properties can be transferred from one end to other end very effectively. One can grow the nanotubes onto the carbon fibers, and it will act as an anchor, improve the fiber matrix interface, and a very high dimensional stability one can get when you are growing using it as a reinforcement. This is again a dispersion and dimensional stability of the composite. Now, we have also made some metallic composite by dispersing carbon nanotube. SPS was used, spark plasma sintering, where the total time was hardly 3 minutes. So 3 minutes it was sintered in a copper, and temperature was 650, and you can get a 1% CNT and 5% CNT so uniformly dispersed, and the properties was measured. The hardness have increased very high. Even the electrical conductivity also have improved by dispersing the carbon nanotube into the metal. Now, another interesting properties of carbon nanotube is its field emission properties. Field emission involves the extraction of electron from a solid. So it is a different type of mechanism where the carbon nanotube will act as a field emitter. Earlier, we have seen the carbon, our televisions was very thick, very bulky from the backside. We were using because we were using the cathode ray tube, CRT. But now we are using a field emission effect. The carbon, now our picture tube is very flat. It's no longer a cathode. Earlier, the cathode has to be emit the electrons into a vacuum tube. So very ultra high vacuum is required. But now the materials can emit the electron at low voltages because of the field emission effect. And that's how our flat panel display has come. This is the concept of a carbon nanotubes. It can emit the electron, and then because it is having a very large aspect ratio, atomically sharp tip, high temperature and chemical stability, because you cannot make any materials in nanometers that sharp mechanically. By any process, you cannot make it. So it is so chemically stable material. If you do it, earlier people were using the tungsten tip, but tungsten tip also used to be a micrometers, and then tungsten was not chemically inert. All those challenges were there. So nanotube has given a very strong set of properties to use it as a field emitter. Now people are talking, if you give a coating of a carbon paste into a plastic sheet, so even a flexible TV also one can get it. So we have developed the aligned carbon nanotube cathodes based on the carbon nanotube, these things. But what happens, the edge carbon always gives a very strong field emission effect. So to make it, we have given a pattern of a carbon nanotube jungle. This was all complete jungle, but we have used we have a very strong laser center. We have used the laser energy to make a different type of pattern. This is a magnified view of that. So the onset temperature of a emission has decreased drastically. So this is a project we have done for DRDO. Now this is a energy related some applications where now energy, now a lot of energy people are using the coal energy, the petrol, which is having a very side effect like greenhouse effects. Many things are there. So people are looking for a renewable energy where the solar energy or the hydel energy or the wind energy should be used more. But all these things are having a challenges. So people are looking for a material which can be used as energy storage devices. So either rechargeable secondary battery or the next generation supercapacitors. These are the two areas of the fuel cell. These are the areas people are looking for energy substitutes. This is the lithium-ion battery, supercapacitor, fuel cell, or the solar panel. In all the four areas, ARCI is working. Now, if you see what is the difference between supercap and the normal batteries, normal supercapacitors, the batteries are having a energy density is high, but the power density is very low, whereas supercap is power density is very, very high, but the energy density is low. Something like, for example, if you have a racer, athlete of 100 meter, it is a very strong person which can give a very high energy impact for a low speed, like a low space running, like 100 meter, 200 meter. But like for marathon, you require a different type of athlete. So now, similarly for batteries, fuel cell, this type of application for supercap, like if you want looking for a missile flying, where the power density required is very, very high, but for a few moments. So you require a supercap, but people for realistic applications, people are looking for a hybrid applications where the supercap and batteries combination should work. Like in China, buses are used which is having a capacitor as well as the fuel cell. The fuel cell in fuel cell or in supercapacitors, the electrode is based on the carbon. The requirement is the requirements are high electrical conductivity, high surface area, the high porosity, and the wide voltage stability. These are the requirements. So now all these requirements cannot be fulfilled by any other material other than carbon. So carbon is used, activated carbon is used here. So here the porous carbon electrode is used, and since it is a very high surface area materials are required, ions will get deposited onto that, and then you will get a very high capacitance. Even the carbon nanotubes, aligned carbon nanotubes are being explored to use as a substrate material. Now we are also working on graphene. Graphene is a material which is a very different type of material, which is having a combination of high electron mobility, very high. The anomalous quantum Hall effect, exceptionally thermal conductivity is really very high, 5,000 watt per meter per Kelvin. The superior mechanical properties modulus is 1.2 terapascal. The surface area is 2,600 meters square per gram. You cannot, tunable band gap. You cannot imagine any other materials which is having a combination of these properties. There are different techniques. Initially the people have those who have won the Nobel Prize, they have used the Scotch tape technique, where they have taken a very strong adhesive tape and tried to peel off from a HOPG, and then get this particular whatever was there, try to isolate them, characterize them, and then found this is a single layer of graphene has come out. Then people have tried even the silicon carbide template method, dissolve the silicon, and then at high temperature, and then get the graphene. Different techniques, people are exploring it, but we are using it as a different format. Like a graphite, we take graphite flakes and chemically intercalate, and then sonicate it, and then each layers, we are presuming that layers will get separated out, and this will convert by vacuum filtration. You will get a bucky paper. Like here it looks the graphite flakes, intercalations, the expanded graphite, if you do the mechanical treatment, and finally the few layer graphene. Depending on your processing, one can get it from 29, 28 layer, 28, 9, 22, even 3 layers also one can get by different set of parameters. This is a graphite. Again, it has to be characterized by Raman and other things to assess the quality of graphene. You can see the carbon material, which is black, but it can absorb almost like a 97.7 transmittance of light is there. So that's the beauty of this material, which is unique by its own. One can make from hydrophobic to hydrophilic by different treatment, this graphene. This also our group is exploring many applications based on that. This is another applications of graphite. As I told you, till now we have seen the graphite which is hard, rigid, but now we are also worked on graphite, flexible graphite, where the graphite flakes is chemically treated, and finally a worm structure, and after pressing into that you will get a flexible graphite. Now the graphite can be rolled like a paper. One can develop a various products out of this, like a gasket. Looks to be very simple, but this is a very highly engineering. Can you imagine a material which can withstand a 500 degrees temperature in an engine, in automobile engine, which should have a ability to compress it, ability to relax when the load is removed. It should be resilience should be there. So no, rubber is very good, but rubber doesn't work more than a particular temperature, 500 degree, impossible. So all this graphite, like seals are there, high temperature seals. This is the seals which is used for wheel and axle plant for casting their wheels. This is a bipolar plate which is used in our fuel cell applications. Fuel cells are the cells which is used where the one channel is used for hydrogen, other channel is used for the oxygen. Hydrogen and oxygen is combined to get the energy, and this plate will act as a like anode for one cell and cathode for another cell. That's why it is called bipolar plate. This is a stack of many fuel cell and assembly, and one can get desirable wattage out of that. These are the few graphite bipolar plates which is having a set of these properties. Another applications which we are working on in the oil absorption, like oil spills are there, unknowingly, knowingly, sometimes accident, sometimes terrorist attack. So these type of oils are not very good for sea. The marine life will get destroyed. Tourism can get destroyed. We have developed this exfoliated graphite, a special type of graphite, which is having a different type of pores, and different these pores can absorb the oil selectively, only oil from the oil water mixture. This is like this. This is the oil, and it is oil and water. It is just sprayed. You can get absorb the oil water mixture. Oil can be about 78 ml per gram. It can absorb. This we have, and then you can recover back the oil also. And this all this product technology was transferred to industry, and industry is now working in Hyderabad for many years. It was a part of our technology incubation part. Now I'm in the last slide. As I told you, the visions and all those things. This man has having a prediction in 1954 that computer in 2004 computer will be like this, because in those days computer was like a very, very strange entity. No one was knowing how the computer will be, but this man has predicted that in 1954 he has predicted computer will be like this in 2004. But we have computer like this now, which can be like a laptop or palm top or and whatnot. So his predictions is no longer valid. But similarly, people are predicting that based on the carbon nanotube, we can make a space elevator, which can go without any support. You can make it an elevator from Earth to the space with based on the carbon nanotube. These are the predictions. How long it will be, whether we could able to do or not do, the only time will tell, because whatever we know is very small. Many things are unknown. So these unknown things, we have to explore it. All the researchers across the globe are trying to explore the materials properties. Our group is exploring the carbon properties, because what is happening one way is many people are working just since others are working, we also want to work it. That's why how we are working. That's why we also have to work it. But my approach is always let it be unique. Is not need not be what others are following. We have to be unique in our approach. Let whatever the output is important. The ultimately we are not working for others. We are working for output. So output is important. And many times we are looking from outside to explore the solutions, but 90% solutions are lying with us only. We have the solutions, all the resources, capabilities. Indians are no way inferior. Only thing is we have to exploit ourselves. We have to utilize full with our full potential. Thank you very much for wonderful listening, and thank you once again, the university, for giving the opportunity. If any questions are there, I will be happy to answer that. Over to Dr. Kavita.
Madam. Thank you, sir. Thank you very much, sir. Now I request Lieutenant Dr. Kavita. Dr. Lieutenant Kavita. So, Kiran sir, I'm very thankful to you, sir. It was a very informative session. Your presentation was very nice, with pictures, and you have given live examples which we are using in our daily life also. And including that, we have shown pictures related to carbon graphite applications in army sites, and with that, many participants who are doing research will be benefited by your presentation, sir. Thank you very much, sir. And there are some 3 or 4 questions which are raised by the participants. Shall I give the questions, sir?
Yeah. As per your program, if you want the question to be now, no, absolutely no problem. I'm comfortable.
Only 3 questions are there, sir. What is most beneficial method for preparation?
You are a little louder. Your mic is
What is most beneficiary method for preparation of nanomaterials?
Madam,
which nanomaterials?
Madam, since Kiran sir is ready for the
presentation.
Okay.
Yeah, because it's already late for sir.
So Dr. Kavita, you can just note down the questions. You can
okay, sir.
Me. I will give
Okay.
all the question answer. Absolutely no problem.
Okay, sir.
Yeah, let
Okay,
us
thank you
listen
very much.
Sir will spend some
Thank
time
you.
for questions in the end. So,
Thank you. Thank you.
Okay, okay. I'll send you, sir. I'll send you, sir.
Yeah, right. Thank you. Thanks a
Okay.
lot.
Thank you, sir. Thank you very much. Now, I request Professor B. Prasanna, sir, to
Madam.
introduce our next speaker,
Yeah, sure, madam.
Dr. Kiran Solingapuram.
Sir, thank you, madam, for giving this opportunity. It's my pleasure to introduce today's our eminent speaker, Dr. Kiran Kumar Solingapuram Sai. Presently, is working as assistant professor in the Department of Radiology at Wake Forest School of Medicine, Medical Center, Winston. Presently, I would like to tell his journey briefly. He did his post-graduation at Usman University and completed doctoral research at Northern Illinois University. And also he was awarded postdoctoral research at Mellington Institute of Radiology, Washington University of St. Louis. He acts as a reviewer for funding agencies. The first one is the Basler Foundation at St. Louis in the year of 2015 and Tobacco Control Center of Excellence, Wake Forest School of Medicine, Winston-Salem in the year of 2018. Earlier, he was Friends for an Earlier Breast Cancer Education, NC, in the year of 2020. He is a member of editorial boards and reviewers in reputed journals. He received plenty of grants from different agencies international. He has completed 2 patents and more than 40 publications in the national and international journals, and also actively involved in the scientific presentations at national scientific conferences more than for 68. This is just very briefly introduction about the Kiran Sai. Sir, thank you for giving this opportunity. Now I would like to invite Dr. Kiran Kumar Sai sir to explain the topic on PET imaging of novel biomarkers for early detection of neurological disorders of cancer. Thank you, sir. Sir.
All right, thank you. Can you all hear me?
Yes, sir.
Great. Yes. So before we even start, a big thanks to Chaitanya University, and especially thanks to Professor Kavita Garu and you, Mr. Prasanna. Thank you so very much for having me here. It's a pleasure to talk to all our folks, and a big thanks to Professor Jain for giving a wonderful talk. It was like an eye-opening, a big picture application for a lot of nanomaterial science in different aspects. Here I am. I mean, again, this is a complete 90 degrees overturn of a different topic here. It's good to have a diverse topics, and then that's how things might be turning interesting. So this is here talking about PET imaging of novel biomarkers for neurological and oncological applications. As Dr. Prasanna mentioned, I'm a faculty here at Wake Forest School of Medicine for almost 5 years. This is my 6th year now. So this is my outline. I'm going to talk about some introduction with the PET imaging. So positron emission tomography imaging, why is it so important? And I'm going to talk into 2 different aspects of neurodegenerative diseases and cancer, and then some other cool studies that we do at Wake, which is very unique in my group. So what exactly is this PET imaging? I mean, often people think when I say PET imaging, I image animals. So it's not the PET we are talking about. We are talking about positron emission tomography imaging. That's very, very important part of imaging. The one which is more sensitive after, in fact, it's more sensitive than the MR, because MR and CT will only give you the structural aspects, whereas the PET will give you the functional aspects, which are quite important to really diagnose a disease or even for your therapeutic applications. So as you can see here, this is a non-invasive method and very unique that you will get the entire body's biochemistry and functions. So what you need to get a PET image is a cyclotron. Cyclotron is something that will make your radioactive isotopes. As you can see here, these radioactive isotopes emit a positron, positively charged electron. And this positron, when it collides an electron from the body, it emits 2 gamma rays. As you can see here, a subject is lying in the PET scanner, and once the PET isotope is injected, the PET radionuclide collides with the electron of the body, emitting the gamma rays, and that's how you see an image. So the most commonly used isotopes in our case are the C11 and F18 isotopes, as these are again generated from the cyclotron, and C11 has a half-life of 20 minutes and F18 has a half-life of 120 minutes. Like I was mentioning, this is the big picture nucleides for the PET, and commonly we use are F18 and C11, 20 minutes and 109 minutes for the half-life. So this being a chemistry talk, I really wanted to introduce some organic chemistry synthons in between instead of giving you the big picture overview of the applications. As you can see here, these are all the different synthons where we use for radio labeling a precursor or small molecule. Among them, the most commonly used synthons are the methyl iodide here and the methyl triflate here. So a simple chemistry reaction, what we do is we start with the radioactive carbon dioxide. Upon nickel and catalyst, a simple reaction under the catalyst gives you a methane, and the methane under iodine reaction gives you a methyl iodide. If you want a methyl iodide as your methylating agent, that's what you use. And if you want a more stronger reagent like methyl triflate, you pass the methyl iodide through a silver triflate column. And this is a simple, again, an F18. How do you make, see, in the case of C11, it is electrophilic reactions, whereas in the F18, commonly we use F18 as a nucleophilic substitution reaction. So this is a simple reaction. What happens is the F18 comes from the O18 water, that's from the cyclotron. And then in the water, in the heavy water, the F18 is being bombarded, and then you collect the F18 on the resin, and then you remove all the O18 water, your heavy water. So once the F18 is trapped on the resin, you wash with your potassium carbonate and the K22. It is a cryptofrax. This is like a coordination chemistry again. It will trap your F18 inside the K22, and then you elute your F18 minus from the resin using your basic solution. So this is what we do in a big picture. Like I was telling you, you see a picture here, but what goes behind the picture is what we do in my lab. So this is your PET imaging positron camera. So we start with your cyclotron, what emits your isotope. And this isotope coming from the cyclotron is used for a radio labeling reaction. And then once the precursor is used and we make a radio labeling reaction, then your final product is being injected into the subject. So that's your cartoon, and this is the real time. So this is what we have it in our lab at Wake Forest. So this is your cyclotron, which makes your isotopes, and this is pumped directly into the hot cell directly. We don't have to go in there. It's all grounded. So it comes from the underground, the 4 active sets, and these active hot cells are made up of lead to prevent any radioactive safety thing. And then inside these hot cells, we have this 4 different radiochemistry units. So the wonderful thing with our thing is we don't put our hands at all. So it's all well automated. So it's all computerized systems. So it's all operates with the computer. So we give the program and these things move up and down. And this is for every synthesis, you have a separate program written, and we close the hot cell doors, and then that's how the reaction happens. As you can see here, inside these hot cells, these units are present, and we have this lead big hand using systems that we can use to move the radioactive isotope from the hot cell. And again, before we inject anything into the subject, we have to do a QC. And this is what we have here. Like we have a GC and your HPLC system. We also do the bacterial endotoxin testing and your sterility testing before we release the product for any clinical research or even for monkey research. So these are our scanners. That's we have a PET scanner, the GE64 slice. And the same thing here, we do it for humans and monkeys, dogs. All this research happens here with this big scanner, and a miniature version of the same thing where we do the micro PET. That is, we scan the mice and rats, and sometimes we even scan the ferrets. So we scan all the smaller animals here with the same version here, and these 2 are MR scanners exclusively for research. And right now we also have a GMP room because whatever we do is for clinical research, and FDA mandates to have this GMP facility. So everyone has to get completely dressed up with all the PPE to enter into my suite. So like I was telling you, it's very important for any drug discovery that you identify a lead, and then like a typical drug discovery lab. So you learn from your research, right? Literally, not every research goes through to successfully or fruitfully. So all the failures has to be noted, and then you go back, identify the target, Again, you validate, do your in vitro binding assays, and then for us, you radio label with the isotopes, and then you do it with first in the preclinical imaging modality, like using the mice, monkeys, all the animal models, and then you go for your clinical trials. Again, this is a process of a cycling. It's a cycle. Like you learn out of your mistakes and you go back and identify a new research. So this is how you identify unification for the basic and clinical research. So this is all your basic research, and this is your clinical research. So here at Wake Forest, we do everything. Like we start from a simple preclinical process. We make the system very much automated, and then we manufacture the drug. We do validation runs. So this is RDR proposing something. We do it for the FDA. FDA is needed for us to do some proposal before we submit an application, making sure the drug we make is safe for all the subjects. And then finally, we go into the clinical setting. And the whole purpose is for early diagnosis or for therapeutic applications. So we do all for different areas of science in our facility. We do cardiology, we do for dementia, metabolism, neuroscience, oncology. So we do, like I was telling you, we do all different, like whole 9 yards. We start with the chemistry, we do some small animal research, large animals, and then do for clinical trials. So with that brief introduction, just to make sure we all speak the same language for another 40-45 minutes, I'll go with my first topic of identifying the neurodegenerative diseases. So this is a very favorite slide of mine. I mean, before we talk about the neurological disorders, the first thing comes is your Alzheimer's. So my old research, like at least a good part of my research is on Alzheimer's. In fact, my recent funding from the NIH is on identifying early tool of diagnosis for Alzheimer's. So what is Alzheimer's? As people in India especially think like memory loss is common with the age, but not really. I mean, like we have all the symptoms, but people don't name it as Alzheimer's. So here, as you see here, memory loss, change in mood, misplacing your belongings, hard to complete a familiar task. When you think these things are happening, you are having an early symptom for Alzheimer's. Confusion of time and place. Do not associate these things to your age. I have seen patients here who's 90 years with perfect memory. So he does not have Alzheimer's. Just because you are getting old, it doesn't mean you need to have a dementia or memory loss. So these are all the early symptoms of Alzheimer's, making you think like, yes, you have something going on in your brain. How do you avoid those things? So this is an inside picture of your brain. What happens in the healthy brain? As you can see here, everything is intact. Your neuron and your brain has a three-dimensional structure perfectly well. Whereas in the Alzheimer brain, as most of the peptides get associated to form into a plaque or tangles, it could be A beta or your tau proteins. Those are the two characteristic proteins that are overexpressed in the Alzheimer brain when compared to the normal brain. See here, this is a normal neuron. Everything is fine. Here, as you can see here, the amyloid plaques and the neurofibrillary tangles, the tau peptides, are overly accumulated, resulting in the poor brain function. So why is it important to study Alzheimer's? Especially, I mean, here in our country, where we start with 5 million people, and now it's projected to be 14 million people are suffering with Alzheimer's disease. It's very hard to see your own people going through a lot of things where we will see like the person forgets his own name. I mean, like that is a terrible thing to go with, like where you forget your own name. So that's all like, I mean, with the status or within the big umbrella of Alzheimer's disease. So there is a serious issue going on. And unfortunately, I couldn't find the same number for Indian population. And this is again with the projected population of US. Like currently, this is how the people getting dementia in lower or middle income countries. Like I bet like one of this should be within India as well. From 2015 to 2050, this is how the low and middle class income countries will raise with number of Alzheimer cases. And this is again the projected surveillance or the prevalence with the Alzheimer cases. So the problem with Alzheimer's is we do not have a cure. Unfortunately, there is no perfect cure for Alzheimer's. So early diagnosis is a bigger picture question that needs to be answered to understand the pathogenesis of Alzheimer's disease. So overview of my research with the Alzheimer's disease is what we done is GSK3 inhibitor tracer, microtubule tracers, and other important PET radio tracers that we developed. So before I come into my microtubule picture, we started our research with identifying something called glycogen synthase kinase inhibitors. As you can see here, in a perfect picture, everything should be stabilized. Your tau is very much intact. We need tau proteins, and the tau needs to be associated with your microtubule that stabilizes the three-dimensional conformation of your axon. So this is very important for the messages to be transferred from the body, from the brain to all the parts of your other organelles. But what happens in the Alzheimer case is your kinases. I mean, this is what overly phosphorylates the tau proteins, resulting in hyperphosphorylation. And then hence your microtubule gets depolymerized, forming the polyhelical filaments. So your GSK3 is one of an important kinases that plays a big role in doing this performance of Alzheimer's, where it's hyperphosphorylated at multiple sites. So with the GSK3 inhibitors, this is a lot of big biomolecule or a biomarker for several diseases. As you can see here, multiple avenues have been used for neuroinflammation, peripheral inflammation, like in cancer, diabetes. People are using in and out all these GSK3 inhibitors. And now we are using this as in the brain. So it's a therapeutic target for neuropsychiatric and degenerative diseases, mood stabilizers, antidepressants, and lastly, a lot of CNS, central nervous system disorders are being associated with the GSK3 kinase thing. So it's very important. I mean, why do you need to image it? So that will tell you like how much of GSK3 is present in the normal and the diseased person, and if the drugs being used are really being effective to treat it. So far, there is no validated PET radio tracer for quantifying the GSK3. So in that angle, this is all the different researchers have been used. The problem with all these molecules was there was a fast washout in the brain, significant non-specific binding, and homogeneous distribution. So obviously you want your compound to be specific for a biomolecule or a big tracer. So, and importantly, there was low blood-brain barrier penetration, meaning this couldn't go into the brain and stick. So if it doesn't go in the brain, the purpose of labeling them is not very successful in the bigger picture. So this is our molecule that we developed in the lab. So this is one of the GSK3 ligand, A10707222. So what we have done is, as a radiochemist, so we look for a group that can be easily methylated. So as you can see here, the methoxy group is here, where what we can do is like we can substitute this methyl group with the radioactive methyl group, adding your C11, and that becomes your radio tracer. So simple radiochemistry here. Again, we make this phenolic compound. This phenolic compound undergoes a radioactive methylation with the C11 methyl iodide that comes from the cyclotron. And we add that here under sodium hydroxide, giving us a radioactive methoxy compound. And this is what makes the PET image. So when you inject, we'll see what happens into the thing. So we have successfully automated it. The purity is high, and this is specific activity. So what specific activity is, you need to have more of radioactivity, that is more of C11 and less of C12. C12 is your normal thing. So it's not like you're creating a new thing. It's just atomic reactions. So isotope stability and instability. So you need to have more of radioactive and less of non-radioactive substance to get a good image of anything that you're imaging. So this is like, look at this. This is like so much of radioactivity per micromole of the same compound. So which is showing us that this compound is made in high activities. So what we have done, this is a monkey image. So we have shown in monkeys, this is like a healthy monkeys. We have scanned their brains, and this is what are we getting it, that it goes into the brain. Now, currently we are looking, this is a normal healthy monkey. So we are comparing that to an Alzheimer monkey. So here at Wake Forest, we almost have like 300 to 400 monkeys in our research suite. And we have research going on from addiction, neurological disorders, cancer, a lot of things. And we scan their brains to understand the mechanisms in the big picture. So that because monkeys are, the non-human primates are very close to humans, and this is a perfect tool to understand any research with relating to drug. So this really shows that it goes into the brain and sticks for at least 90 minutes. So this is a washout kinetics here, and this is the different regions of the brain that goes, the GSK, A1 compound, and the distribution is very well formulated with the available densities, meaning it will go and sit in areas where there is a lot of GSK. So that again shows that this compound is your GSK specific. Like I was telling you, we are doing other studies currently while we are doing with the monkey blood metabolites. So we also, like any drug company, we have to understand what is happening to the new drug, how much amount of the compound is staying in the blood, how much of compound is decomposing by 90 minutes. So because these are all radioactive compounds, so the half-life is only 20 minutes. So we should make sure, like at least for 4 half-lives, everything is being washed out. So by 90 to 100 minutes, you always want to make sure that it's almost coming to a baseline. As you can see here, this is the original blood curve, and this is the amount that we have collected and seeing in the outside. This is to our ex vivo, and this is your in vivo curve. So these are again a different distribution volume of the brain with different regions like your occipital campus, the hippocampus, cerebellum, caudate, and all. So as you can see here, anterior cingulate has the higher uptake of the tracer, which is very well inclined with the GSK tracer availability. So far we have made it, again, so this is again, I'm telling you a story of how we did in the lab. So while we were doing it, we synthesized it, we have successfully shown that it goes into the brain and it has a heterogeneous binding, which is good. Not the whole brain is lighting up. So it is going up well in the accordance to the GSK thing. So right now we are working with other imaging targets. And again, RDRC means we are going for a clinical trial. So we are going to put this drug in people soon. So this is how research. You always have to think beyond it. So once we finished with your GSK, we want to see what happens later. So, what's inside the box? So we have seen and understood the GSK, and we want to see what happens behind the GSK. So like I was telling you, the function of GSK was with the microtubule and the tau associations. So that's when I got an idea of why not imaging the microtubule itself. So while I was digging the literature, what we found are these microtubules are the cycloskeleton polymers comprising of several repeating covalent and non-covalent bond alpha and beta subunits. As you can see here, they're very important part of healthy neuron systems. So throughout the system, they have been present. Like I can see here, in a healthy microtubule, everything is well stabilized. So the structure is well integrated and everything is completely closed. What happens in an Alzheimer's disease? The microtubule is heavily disintegrated or hyperphosphorylated, leading to disintegrated microtubules, as you can see here. So what we found with the literature was not just in Alzheimer's diseases. Look at the number of diseases that have been implicated because of destruction of microtubules. So you name it, they have it. Any disease, we found like microtubules are heavily disintegrated. That's the first thing happening in the brain, that any dementia problem, inflammation problem, injury, your spinal cord injury, or even ALS or HSP, anything happens in the brain, the things is the microtubules are the first thing that's getting implicated. Again, this is telling you back the same story with a healthy brain and Alzheimer's brain. So currently what is the problem is we do have some imaging tracers. Like I was telling you, the two characteristics are your plaques and your tau. So we do a lot of clinical trials. For the A-beta, that is your amyloid beta thing, we have the PIP scans. We do it all the time in our hospital in my clinical patients. So when you compare with the normal, so this is a normal person's brain and this is your Alzheimer's brain. Look at all the red things. So red things means there is a lot of amyloid beta. As you can see, there is higher uptake of the red, showing that there is something going on with this particular subject's brain. So it does tell you that there is, so this is already available in the picture. Same thing with the tau. So this is a normal person and this is an MCI. So this is cognitively inclined. So this is another distinguishing disease when compared to AD. AD is having a lot of symptoms, and this is cognitively declined, is like not completely up to the level of AD. They do have some memory losses. But as you can see here, in an AD, you see a higher loads of tau, whereas in the normal person, you don't see the same thing. But the problem is all these will only come into picture with the late, meaning like you already have it. So what is the purpose of knowing it when you already have it? I mean, there is no cure. Of course, they will have to change with interventions. So there is no tool currently available to see it in the early pictures itself, like in the early stages itself. So it's very important to understand the biomarkers or capture the changes in the brain, especially in the context of AD, A beta, and tau. So, so one step back is to understand what is happening inside the brain before even the A beta and tau forms. So that's when we thought of having a microtubule binding agent. So especially when we were looking at the research, we did not find anything that goes in the brain. So a blood-brain barrier penetrating PET ligand that will quantify the microtubules non-invasively would permit imaging of a lot of diseases. I mean, not just Alzheimer's, ALS, Parkinson's disease, Sjogren's disease, or your spinal cord diseases. You can really use this particular microtubule agent. So we went back into our literature. We found that all this paclitaxel, these are the common drugs for the cancer. So people have already labeled it. As you can see, they have put F18 isotope here, C11 isotope here, and also here you can see the C11 isotope here. So the research has been done with all these radioactive substances to identify what's happening in the brain and all. But unfortunately, if you see the same results, nothing goes in the brain. The brain is almost like empty, zero or no, very little uptake in the brain or no uptake in the brain. So therefore, these microtubule agents are not really useful for any of the Alzheimer's diseases because everything is with the brain. So far in the literature, we haven't found a microtubule agent that goes in the brain. So that's where our strategy. So this is our compound that we developed called MPC6827. And again, as a radiochemist, we look for compounds that can be easily methylated. So we have this O-methoxy group. As you can see, look at the affinity. It's 1.5 nanomolars for microtubule, whereas all the other targets in the brain has greater than 10,000, showing that whatever compound we made in the lab is very, very specific for a particular microtubule. And more importantly, there is a lot of literature. People have used this compound similar ways for other diseases, especially for cancer, as a GBM, glioblastoma drug. So, but as a radiochemist, we want to see whether it can be used as an imaging agent. Again, a simple radiochemistry here from methoxy group, that is a phenol group, converted into a radioactive methylation group. This is done all again in the GE synthesizer, greater specific activity of 3020 millicuries of radioactivity per micromole of the substance, which is an important thing to follow and move forward. Excuse me. So here you go. This is like our image catcher. So this is just the normal brains of the mice. So we inject the compound, whatever we made, and look at it. I mean, like I was telling you, more red is more compound. So it clearly goes into the brain. So this is the first compound that goes into the brain, first microtubule agent that goes into the brain. And as you can see, this is just the mice and this is a rat. And why do we compare with this one? So what we have done here is this is a mice that got pre-injected with the same compound. So naturally, when you pre-inject your compound, before you inject the radioactive compound, everything is completely blocked, right? So the receptors are completely blocked. And when you inject a new drug, you should see a decreased uptake because the whole receptors are completely blocked. So that's what we see here. I mean, greater than 90% is blocking. So showing that your compound is very specific. So this is the original baseline thing, and we block with other microtubule agents. As it decreases more than 80%, it shows that what you made is very much specific for microtubules. And this is your first blood-brain barrier penetrating PET ligand for microtubules. And this is the biodistribution. For any drugs, we need to make sure the compound is stable at different time points. So we do like 4 mice per each or 5 mice per each time points. We sack them and we see what's happening in their brain, blood, heart, liver, lungs, spleen, pancreas, kidneys, and muscle. Like I was telling you, this is again a typical radio distribution thing that we do for every radio tracer. But very importantly, as you see in the brain thing, by 60 minutes, everything is washed away, which is good. And same thing with the brain, I mean, blocking. So some of the animals, we blocked it by injecting a cold compound, non-radioactive before, and you can see greater than 80% blocking, showing that this is specific. So like as a chemist, you always want to improve your own targets. So this is the first generation. Now we already finished the second generation drug. We thought this would be much better than the first one, but the IC50 is around 3.25 nanomolar, which is not bad again. So we did the same radiochemistry thing with the phenol converted into methoxy group with the same methylation chemistry and automated and everything. This is again, now we have two radioligands. We blocked it with the two non-radioactive compounds. The uptake decreased, again, goes very well in the mice brain. And as you can see here, this is the baseline, and these two are the blocking uptake. So clearly shows that it does go into the brain and it does lower as you want. Same thing, we did the biodistribution. We sacked the mice at different time points, but by end of 60 minutes, it is going low. Every compound has a different fate in the in vivo. It doesn't have to be the same way like previous compound, but it is almost, I mean, if you see a profile of the MPC, it has a different profile, like stepwise reduction of the uptake, but this one has more uptake for 30 minutes and almost going down back to 60 minutes, almost nothing. So it means by 120 minutes, it will wash away from the body. So the next step is obviously we finished mice successfully. We went with the monkeys. So this we published this year in a high impact journal with molecules, where again, more red is more uptake. So this perfectly goes even in the monkeys. So this is the first microtubule imaging agent that goes even in the monkeys. So now we are doing AD monkeys, like I was telling you, we are doing a research. We are comparing the uptake with the normal monkeys with the Alzheimer monkeys and see if there is a difference, and then we'll go into humans. So again, this is third generation in the lab. We are again doing the third generation drug. So this is baseline and again blocking to show the specificity, similar radiochemistry again. So our microtubule story. So how do you do it? So far we have successfully identified a ligand. That's good. Did we do the radiochemistry? Yes, we have successfully did it, and we automated the entire system. And we have shown that it goes into the brain successfully in normal mice and normal non-human primates. When I say non-human primates, I'm talking about the monkeys research we did here. And we already did the second and third generation. Okay, but what next? What are you trying to hit? Is to see whether this will change in your Alzheimer's story, right? I mean, that's the whole purpose of doing the microtubule imaging research. So this is again bringing back you the same slide, showing that it's the microtubule disintegration or dysregulation is well implicated in Alzheimer's disease. So what is our hypothesis here? We believe that the microtubules are stable in the normal brain, and as the brain gets Alzheimer's, all this gets detached and you will see all the detangled microtubules. So currently we only have two traces, that is the A-beta tracer and the tau tracer, and both are only playing a role only when the disease comes, when we already have the symptoms, like way later in the picture. So we want something that can do the symptoms early on. That's like an important aspect of AD. So currently there are no imaging traces available to predict the disease early on in the picture, not very late in the picture. So what we have done is, as the first thing, we have to do it in the mice. So we have some mice also having Alzheimer's disease. So we have picked those mice which has overexpression of amyloid beta, and some of the mice which has overexpression of the tau. So we have sliced their brain, and we have shown that this is again a normal brain of the mice, and this is a normal brain of a Alzheimer's mice, and look at all the amyloid beta it has. So this really shows that we already have the amyloid beta. Same thing with the P301. This is the normal mice, and the same mice as it gets old, look at all the tau expressions it has in the hippocampus and the cortex areas. So we are showing here that what we pick is the right mice, meaning to show that when we compare two different mice, we want to make sure that one mice has no Alzheimer's A-beta and the other has more A-beta. So now we picked this mice and we started injecting our tracer. So this is your wild type mice. Look at all the uptake, so much uptake in a normal wild type mice. The same compound, when it was given to an Alzheimer's mice, look at all the uptake. It's got reduced significantly. So this is 18 months, which has normal mice, and this is the Alzheimer's mice, and this is an Alzheimer's mice at 22 months. Within 4 months, the tracer uptake has been lowered like anything. When you compare to the wild, look at all the mice uptake in both the cortex to the hippocampus areas. So this really shows that whatever tracer we made is really good. I mean, meaning it is showing a difference in uptake. And early on itself, we can show the same thing. So what we have done is, can we predict the same thing from 3 months? So what we did a longitudinal study. At 3 months, the same animal uptake is here, and 18 months, the same animal uptake is here, and 22 months, the uptake is here. The same compound can show a variation of the brain uptake differentially, showing that whatever compound we made, the MPC 6827, is very well inclined for targeting the microtubules. So this is again another imaging, this is 5XFAD, another mouse model of Alzheimer's. So transgenic has more Alzheimer's A beta, and look at the uptake, significant decrease of uptakes. That's 15 months. So this is of the mice age, and it has so much of A beta. Because of so much of A beta, the uptake has gone down significantly. And then importantly, not just in the A beta mice, look at the tau mice, meaning these are the mice, if you remember my slide here, this is the same animal I'm talking about. A beta is here and tau is here. So in both the animals, when I did the injections of my tracer, this is what I'm seeing. So at 5 months, this is the uptake, and the same animal at 13 months, no uptake. So whatever compound we made is doing something in the brain. So now we have to identify what's happening in the brain in a bigger picture to see that this is a change happening, or can we predict it early on itself. The reason why this is so happy is, like, I mean, look at the transgenic at 5 months itself. So this can predict the brain changes early on. So now what we are doing is we are testing the mice with different behavioral aspects. So we have the memory test for the mice. We do their behavioral aspect. How is it impact his cognition? How is it interacting with other mice? So everything is being tested right now in the lab. So we can correlate the uptake with the outcome of their cognition. So far we have concluded all these things, that we made the compound. See, as you can see, as the A beta uptake increases, the A beta or tau load increases, the uptake of our compound decreases. So this is not just the imaging, even the biodistribution said the same thing. So now we are testing with more amount of mice. We are doing more amount of different mice models. Like I was telling you, we are relating this with the cognition of the mice. We are talking about the behavior of the mice and then understanding it. We are working in the first human clinical trial right now because we have finished successfully with the mice, and parallelly I'm working on the monkeys. So before I go to the next step, I do want to reiterate a few of the points of the Alzheimer's disease. How do you prevent it? Like I was telling you, there is no cure. So talking about Alzheimer's, early diagnosis, and how do you really, in a bigger picture, to avoid the whole dementia thing is, again, the 6 different steps are regular exercise, social engagement. Of course, it might not be possible right now with the COVID situation, but again, your healthy habits are very important. Mental stimulation, quality sleep. I mean, I have reinforced all my people, my subjects, and my patients, saying that your sleep is very important parameter, and your stress management. Because a new study from our Wake Forest has shown that a person who is having at least a good sound 6 to 7 hours sleep has shown improvement in the cognition. So people having problems with the memory, if you sleep well, you will see that you will have a good memory and you will not have any issues with your mental issues. So it's very important, because at the sleep, that's the body's natural mechanism to remove or wash out your tangles. Look at the beauty of the body. I mean, I'm just reiterating the old school topics, that a good sleep is an important aspect. So this is again a small things I want to reiterate everyone, like even if it is in the COVID situation, follow the 5 different things. Look after your heart, be active, follow a healthy diet, chat. You always need to challenge your brain, puzzle it up, and then see what happens. Again, when I'm saying social activity, this is before the Corona thing, but yet I would still want you guys to have a social activity within your family. That's good. So we have done with the Alzheimer's. So this is another important disease called amyotrophic lateral sclerosis. I hope I have enough time, Dr. Prasanna. Can I still continue?
Yes, sir. Sir,
Okay.
continue.
Okay. So, I mean, I don't want to eat up a lot of time. If people think this is good enough, we can stop here. So this is amyotrophic lateral sclerosis. This is an important disease again. So the problem with this disease is there is, again, no cure. thing is the whole motor neurons gets infected, meaning like you cannot do any function. You are sitting on the wheelchair for your life. Your things doesn't work at all. I mean, I don't know how many people remember, what is that movie of Shah Rukh Khan, that girl, Anushka Sharma's, I mean, something where the girl is on the chair throughout. So that's like that she goes with the same disease called ALS. So your whole motor system is completely shattered. So your spinal cord is an important aspect of that, because that's where you control your motors system, and that's being shattered in an ALS. It's a very, very, very bad disease to have. Like your whole physical activities are being shattered completely here. So there is no current cure with the thing, and hence people are looking at the diagnostic tool. So again, what we have seen that even in the ALS, there is a loss of microtubule. So we used that and thought, like, why don't we use the same agent to see whether we can use our microtubule agent as a marker for ALS as well. Again, so to start with anything, we need to use the mice model. And this is the normal mice, and this is your SOD mice. SOD mice is something which shows the overexpression of the ALS. So, and like you say here, this is a normal animal, this is the ALS animal. It has overexpression of the ALS, showing that whatever SOD mice we took is a perfect model for looking at the thing. So this is a simple example. See, you look at your wild type mice and look at your SOD mice. So much of uptake with the normal mice of the same age, and we took the same animal, the same aged ALS mice. So there is no uptake. So it also shows you that there is something happening with the microtubule pretty much in all the neurodegenerative diseases, not just in Alzheimer's, but also in the your ALS as well. But importantly, I would want to point out that ALS is not a big brain disease. Look at your spinal cord. Even here, this is what happens in the ALS. Your spinal cord is the one that gets implicated. So like I was mentioning you, not just in your wild type of your brain, your spinal cord uptake is also being lowered. And as a rule of thumb, when we see people here with an ALS symptom, the first thing what we ask is, are you able to put your key in your vehicle and able to turn? If you cannot turn your vehicle, that's like a rule of thumb. That's when you start rejecting, like people are having ALS. So if you cannot really turn your key on in your vehicle, it could be a car or your two-wheeler, it shows that you are ready, something is going on. Your motor nerves are not enabling you to do your normal activity, and you're switching your car keys and your vehicle keys. If it doesn't happen to you, then something is wrong. That's when your ALS is started. So again, we are working on the ALS mice model as well to see what is happening in a big picture. Completely switching gears. I mean, my lab also does equal amount of work with the cancer as well. So when I say cancer, I mean, people have done enormous work with imaging cancer in different strategies. So one of the important strategies that I'm going to show you is my reactive oxygen species. And very importantly, what I took is your ascorbic acid, that's your vitamin C. And how can we use that to really see with the imaging the oxidative stress or the reactive oxygen species. I'm not going to talk about this because I believe everybody knows the reactive oxygen species are overexpression. See, normally you need them for all the functions, but the moment they become overly highly expressed, we have issues. So several diseases have been shown implicated with the deleterious effects of high amounts of reactive oxygen species. Look at this: the cancer, Alzheimer's, DNA damage, amino acid oxidation, cardiovascular functions, like your even heart attack. So you see pretty much any disease, there is a lot of reactive oxygen species. Even your addiction, I mean, I don't know how many, that's another topic I can talk for an hour. So even in those cases, you will see a lot of reactive oxygen species. Your cigarette smoking, all your alcohol thing will create a lot of increased free radical ions in the brain. So this is again a favorite cartoon to tell you, like, every organ in the body is being implicated with the oxidative stress. Oxidative stress is something when you have an imbalance with the normal amount of free radical species. You always need to have a normal balance. If it is going high of free radical or the reactive oxygen species, you will get problems with all your parts. So due to their critical role, anything that you want to do to lower the oxidative stress will benefit the whole clinical research. So the problem so far with the oxidative stresses, people have done research to identify a lot of imaging thing. That people have used the chemiluminescent, that is the redox cycling. People have used the enzymatic probes, but all of them have problems because the reactive oxygen species itself are very short-lived and they're very reactive. The name itself will tell you they're very reactive. To really capture them at one particular oxidation state is really challenging. So you really need to have something that really captures the whole thing, and again, without no side effects. So the problem is, so far people have used dyes, like the radioactive dyes have been used, but then it didn't go with the clinical trials because some of the dyes are carcinogenic. You can't inject a dye into people and say this is your drug. No, that's not going to happen. So we really need to find out a sensitive thing that will detect earlier reactive oxygen species at the low level. So there is an unmet need to find out the whole thing. Again, this is the same slide. Want to repeat that so many parts have been implicated with high amount of oxidative stress. So far, we have done, we have in the literature, fluorescence, enzymatic, ESR, chemiluminescence, and PET imaging also been reported. But so far, nothing has gone into the clinical world because it has poor target, they have adverse effects, some of them are dye-based, and some of them are highly unstable. Therefore, no clinical applications have been seen. So what my thought was, how about using a vitamin C, like your orange thing? I mean, people have used vitamin C currently for a lot of clinical treatments, meaning for treating the bad effects of your chemo and the radiation, people give high amount of vitamin C. But the problem is only few people see a positive change and few people does not get used with the high dose of vitamin C. So it's good to know early on if this vitamin C treatment will work or if it not work. So one of the application is using one of the, why don't we image vitamin C, that is make the vitamin C into radioactive. Can we make a radioactive vitamin and see if that will help to see if can it show in the cancer model. So that's where we thought of identifying the positive responders early on will help a lot. Like then the person does not have to go through a lot of chemo treatment. Will it work? Will it won't work? So if a drug comes into thing, if you can image the person early on and tell, hey, this is what you're going to get. This is going to work for you. B, if it's not going to work for you. So that's the bigger application. That's a big problem that needs to be solved with the reactive oxygen species. So that's again where we come up with an idea of why don't we label the vitamin C. The 3 reasons why I choose these. It's water soluble and very easily no side effects with vitamin C. It cannot be harm to people at all. And it has already shown that it has anti-cancer effects. So the problem is some people think it is a pro-oxidant. Some people think it's an anti-oxidation. So what we have found in research, that's where my patent holds, is at lower concentration, your vitamin C is a pro-oxidant. It will create radioactive species. Whereas at the higher oxidation sets, it's an antioxidant. So there is always the switch happening. So there is a threshold that needs to be understood. So this is our thing. We selected a compound that's based on the previous literature, but nobody has radioactively made it. So we made the first generation and the second generation drugs. This is all the radiochemistry being involved and the chemistry. We choose the L-ascorbic acid here. And we have completely protected the 1,2 hydroxy groups here, and then finally opened up and did our chemistry on this side of the 3' position here and found a big phenolic group so that we can introduce a radioactive atom. So this is found to be already shown that it has some anti-cancer effects. We took this vitamin C. The only reason we took here elongated is, as you can see here, this is fluorine, right? So we can make this fluorine into F18. Making into radioactive atom and see what happens as a vitamin C radioactive analog. So this is what I was talking. So we made the corresponding precursor, your nucleophilic substitution. All this in microtubule thing, you have learned about electrophilic substitution. Now it's a nucleophilic substitution. where F18 minus will be substituted, and this OTS is an easy leaving group, and that's where you get into F18. Simple radioactive reaction, radiochemistry. Within like an hour and a half, you can 1 hour you can complete the reaction completely and get into formulation. So again, what we have seen successfully is we did some cell uptake assays showing that this is very sensitive. And look at this thing. This is tumor. This is a mice that has the tumor. That is, it has the head and neck cancer. And we have injected the cancer cells in the mice, and we know that there is a tumor here. And when we injected this compound, look at this. I mean, only the image glows with the compound. So this particular compound clearly shows, and naturally we know that this any tumor site has high amount of reactive oxygen species. And the drug you made, the radioactive vitamin you made, when we inject it, it is going into the spot and glowing. So showing that this is very specific to tumor. So now we are doing with other mice model. So what we have done here is we have done in 2 different mice model. So this SSC1 is high ROS and RSC1 is low ROS. Look at the difference. High ROS has high uptake, low ROS has low uptake, meaning whatever compound we made is specific to ROS. Naturally, when there is the high ROS, it's binding too much, and low ROS is binding less. So showing that whatever mechanism the drug is acting on is based on the ROS. So like I was telling you, at low concentrations, it will not kill the cells. It will just bind to the cells. Whereas what we have seen is the same compound at higher concentrations. Look, everything got higher up. And we have seen that the higher concentration, the drug is killing the tumor cells. So at this, there is a concentration threshold for KS1. So it's very important to know that the same compound at lower concentration can be used as a diagnostic tool. The same compound at higher concentration can be used as a therapeutic tool. So this could be an example for a theranostic application, which is therapeutic and diagnosis. So this is the first F18 based derivative at tracer concentrations. Like I was mentioning you, it does not do anything, like it does not generate, whereas at higher concentrations, it does generate the ROS. And this is all my research, and I would like to end my talk with something talking about some other important research that I'm involved with other investigators. So this is an important topic. I know everybody talks about keto diet in India to lose weight, to do things. Actually, it does help. So we are the first one to show with the Alzheimer people that the keto diet appears to prevent the cognitive decline, your brain functions. In the mice have been shown, now we are doing it in the humans too. So can the ketogenic diet help the patients with Alzheimer's disease? So what we have done is, like, we all know what does the ketone. So what happens is body or the brain mechanism is using 2 different energy sources. One is your glucose, one is your ketone body. Whenever you diet, whenever you are starving, or when you don't eat your food, body automatically switches from glucose to ketone bodies. So ketone bodies will become your source of energy then. So naturally, you need to see what happens in a ketogenic diet. What if the person is not given high carbs and given a lot of ketone body? Will the brain use ketone body, and will that help his cognition? So that's what we've been doing. So what we thought is take a ketone body. Acetoacetate is a ketone body in the brain. We have 3 ketone bodies, and one is acetoacetate. One is your acetone, one is your beta hydroxybutyrate, and one is your acetoacetate. So we start people. This is our typical clinical trial. We recruit patients with Alzheimer's, having some dementia problems, and we feed them for 16 weeks keto diet. So before the keto diet, in between the keto diet, and end of the keto diet, we scan their brain to see how is the brain working differently for a person. So this is, again, we have done the same thing in the in the monkeys, showing that it does go into the brain and does all the stuff. So this is a typical radiochemistry here. As you can see here, very smartly, we have used the Grignard reaction or RLI reaction. If you have seen this, if you remember your one-pot reaction where you make your radioactive CO2 and it will form your radioactive carbonic acid thing. And this is what your acetoacetate will be like. Of course, it will be O- here, and you'll always have that in the buffer system. So we are the first one in US to make this radioactive ketone. And this is what we are comparing between a glucose and ketone. So like I was telling you, we do 2 studies in the brain to see like how is the brain switching from glucose to ketone bodies. And we just published this year showing that people eating a ketogenic diet have improved their cognition behavior, meaning their memory has improved a lot. Another last thing I want to talk is my nicotine accumulation study, which I got funded 2017 to study what happens with the brain with the different amount of nicotines, like your e-cigarettes, cigarettes, and all the smoking. So like the whole purpose is people think like electronic cigarette, your e-cigarette is safer than normal, but it is not the case, as you can see here. So we want to prove that a live image of the same thing can be shown. I'm sorry, the slides header is different, but we're talking about e-cigarettes here, showing that the C11 nicotine has been used to see the difference between normal cigarette and the electronic cigarette. So this is how a nicotine is there, and we use a methylation chemistry. We make it, this is a nicotine, and we make it radioactive nicotine. So very smart thing is we make this radioactive nicotine, we put it in the same oil, and we ask people to smoke inside the scanner. So we give them a radioactive nicotine, they smoke inside the scanner. The moment they take first puff, we scan their brains. So this is your typical distribution of their brain. Like I was telling you, more red shows that more uptake of nicotine. And this is what happens with the smoking and vaping. If you smoke a regular cigarette, this is how much radioactivity goes into your brain. And if you vape, that is your electronic cigarette, that's how much radioactivity or how much nicotine goes into the brain. It's almost corresponding. I mean, of course, naturally, when you see brain uptake with your normal cigarette, you will have a lot of brain puff going into the nicotine going into the brain. But look, this is the image that got, I think last year we got the image of the ear with the JNM showing that all your e-cigarette, of course, the brain is okay when we scan people from below the head. Look how hot it is. Your larynx, your trachea, your lungs have so much of nicotine when compared to your traditional cigarette. This is what happens when you smoke, but this is what happens when you do your e-cigarette thing. All your nicotine goes into your thing. And the kinetics are like within 15 seconds, your lungs are having a lot of radioactive nicotine. So right now we are seeing a difference. We want to see whether women and men have a difference, because we are seeing currently with my clinical trial, a lot of women have a lot higher absorption of nicotine when compared to men. So can this be a possible reason for having a lot of cancer thing? So it's just the leading thing that is leading to a lot of addiction problem. So this is all, I think this is my last slide. With as a research, the reason why I showed you multicolor is like different ideas, encourage different ideas. There is like in the bigger picture, everybody is trying to solve one bigger problem of solving it. I mean, how do we make life better? So under one umbrella, different people come and different ideas are being used to solve under one research problem. So we need them entertain new ideas, different ideas. As an educational institute, I do want asking Chaitanya to do the same thing, come up with new ideas, solve the same thing. Even though it's the same problem, come up with a different angle, think differently, how do you solve this? And like I said, naturally, when it takes a town to make a, what do you call, like when in India, there is the saying that it takes a village to have one wedding. So same thing, to make any project successful, I need a lot of collaborators and my team. This is my team here, where currently I have one postdoc and the rest of are all like rural technicians. And my collaborators bring different expertise and external collaborators from other universities. And this is all my current fundings. With the National Institute of Health, I have a lot of pilot funding from different small pilot foundations. And my mentors, my postdoc, my PhD mentor, are all like played a big role to really shape up my career so far. Thank you to all. And this is my team here at Wake Forest, who all work with us. We are all like one team. They don't work for me, they work with me. Just making sure like we all come up with different ideas. And again, never forget my roots. This is where I came from. I went to school at Vaidik at Sitafil Mandi, and then my college was intermediate was in Railway College. I went my BSc in Aurora, and then like MSc in Usmania campus, and here I am. Finally, last but not the least, this is the 3 places where I've been to. So this is my NIU campus, and then I went to WashU for my postdoc. This both shaped a big important role for my career. Here I am currently. In fact, I want to show, this is all Wake Forest in Winston-Salem. This is one side of the campus. Actually, this is where my office is, and we are here underground because everything has cyclotron is a high energy producing unit. It has to be underground. So here we are located. And thank you, my parents, the big role to shape up my career. It is because of them I'm here. And last but not the least, 3 important people in my life playing a big role, my wife and my 2 beautiful girls. Thank you. Thank you all.
Sir, thank you very much, sir, for your given information. Sir, few questions are there.
Sure.
One question is, can you please some knowledge on phthalate derivatives as anti-cancer agents?
I'm sorry, phthalate derivatives? Or
Phthalate derivatives as anti-cancer agents.
I'm sorry. I mean, I don't want to speak up for something else. I do not know a lot about phthalate agents. I'm not familiar how successful are they in a bigger picture. I've heard that it's being used tremendously, but I have not seen a lot of clinical improvement or clinical ramifications. There is no statistical significance with that so far.
Sir, thank you, sir. Sir, another one is there. Optimization of their pharmacological and physicochemical properties led to the identification of CM16 as the lead compound, which is to the best of our knowledge in the first carmine derived beta carboline.
So is that a question or a comment? Are they asking me to comment on that?
No, sir. Question is there. Which is to be the best of our knowledge is the first carmine derived beta carboline for CM16.
Oh, okay. But I'm still confused. Like I haven't spoke about CM16 in my talk. So is that like, okay, that's good. Like if they made a progress on that. So you mean like, there is a group that can be imaged, or I'm sorry, I'm confused here.
Sir, another one is there, sir. Can PET scan find out serum creatine?
Oh yeah, yes. We can image the serum creatine things as well. So the thing is it PET scans, to be honest, are very expensive. To get into a PET scanner is expensive because a lot of infrastructure is needed. So is it really worth? So you always have to think in a bigger picture. What is it going to answer? So if the creatine thing labeling will give you what information will give you that. So that's the reason, like, not everything goes into the clinical realm. So you really have to weigh your chances, whether it is really needed or not. But yes, it has been done, and people are looking the creatine thing in the cancer applications. Yes, very well.
Thank you very much, sir, for your given very informative lecture on PET images and Alzheimer's diseases. And also we learned some how Alzheimer's diseases by 6 pillars. Thank you very much, sir, for your given information. Madam, I would like to
thank you, Kiran, sir. Thank you very much, sir. The session was very informative. And the last slide was very impressive, sir, that all the pillars together building with the different ideas, that what you have said is we have to implement it. We'll all definitely try it, and we'll build a good research center in the Chaitanya Deep University with the different ideas of our colleagues.
Sir,
thank you very much, sir.
Sir, very, very informative.
Thank you.
Thank you, sir. Thank you, sir. Thank you, sir. Now it's time for vote of thanks. I'm profusely thankful to our Chancellor, sir, Dr. C.H.V. Purushottam Reddy, sir, for giving encouragement to conduct all the webinars in the umbrella of Chaitanya Deemed University. And I'm very thankful to Vice President Sri Vikram Reddy, sir, for accepting our invitation and coming over here for this webinar. And I'm also thankful to our Vice Chancellor, Professor G. Damoda, sir, and Registrar, Professor M. Ravinder, for their support in conducting this webinar. And I'm also thankful to our distinguished speakers of this webinar, Dr. P.K. Jain and Dr. Kiran Solingapuram-Sai. Dr. P.K. Jain is from Hyderabad, and Kiran sir is from USA. It is a time which is early morning time for him, I think, in USA, and he has given his valuable time for this lecture on this webinar. I'm very thankful to you, sir, and Jain, sir, for giving your valuable time for our deemed university to conduct a lecture on this webinar. Now, I would like to propose my immense gratitude to Mr. E. Arvind, sir. A very big thanks to E. Arvind, sir, Assistant Professor, Department of Computer Science, Chaitanya Deemed University, for making all necessary arrangements, starting from preparing brochure to the issue of the certificate. Without this, we would not be successful in conducting this webinar. Lastly, I would like to thank all the participants, research scholars, and my colleagues, elders, and all the people who are directly or indirectly involved in supporting the conducting of this webinar. Thank you very much.